Alright, here we are with chapter 4. And this chapter, in most books, is titled Application of the Derivative. And the first half of the chapter, for most textbooks, usually consists of basically using the derivative and sort of trying to sort of mine it for more applications in terms of helping you analyze graphs. Okay, so we're going to harken back to a couple of things that we talked about during Algebra 2 and Pre-Cal in order to sort of make sense out of this, because I foreshadowed a bit of this when we spoke about the analysis of polynomial graphs back in the middle of our Algebra 2 year. Now, if you'll remember, during that time, during that lecture, I would draw something like that. And of course, if you didn't know any better, that probably looks like, a cubic function, right? And I said, okay, this right here is what's called an extreme point, or a maximum, okay? Now, it's not the absolute maximum, and in fact, for this particular function, there's not an absolute, because this keeps going, right? But relative to the points in its immediate vicinity, that is a maximum. That's why we refer to it as a relative maximum or a local maximum. And the same thing with this one right here. This point down here is a minimum. It's not the absolute minimum. For all we know, this one doesn't have an absolute minimum because it just keeps going down over here, right? But relative to the points in its immediate vicinity, locally, it's a minimum, right? Well, what do you notice about both of those? Well, both of those points, since they're right at the top, actually have horizontal tangent lines. And the reason should be relatively simple for us to understand. Basically, it is at its maximum when it stops going up, meaning stops having a positive slope, the moment that it turns around and starts going down, starts having a negative slope. Well, if the slope is not positive, because it's not still going up, and it's not negative, because it's not still going down, it's probably right in between positive and negative, something that we refer to as zero, okay? Same thing down here. This minimum point is where the slope is zero, meaning where it has a horizontal tangent line, because at this point, the slope has ceased to be negative, and has started to be positive. But at the split second that we reach that minimum, I have a horizontal tangent line, and therefore I have a slope of zero. And so if we understand that in terms of what our previous knowledge, in terms of just smooth curves like this that are differentiable, we understand that there is a way to actually get at or find the points at which a function has a zero slope. You would just set the derivative equal to zero, okay? But, unfortunately, things are not that simple, okay? So you can't just set the derivative equal to zero and say, well, they're all my extreme points, because of course there are counterexamples. Let's say I have a function that does this, okay? Is the slope at this point zero? No, the slope here is not zero. The slope here is actually undefined, okay? So in order to find this particular point, I would have to take the derivative and figure out where the derivative is undefined. And where the derivative is undefined, the original function is not differentiable, okay? So here we have two different ways of finding extreme points using our new friend, the derivative function. Okay? We can either find extreme points where the slope is zero, or we can find the extreme points where the slope is undefined. But it gets complicated even more, because not all points where the derivative is zero or undefined are necessarily extreme points. Okay? Because if we have y is equal to x cubed, I know that that function looks something like this, okay? And I know that y prime is 3x squared. What is the derivative at 0? Well, the derivative at 0 is 0. But is that an extreme point? And the answer is no, because the slope doesn't stop being positive and become negative. It stops being positive for a split second and then continues on being positive, okay? So we have to refine our definition of how to find extreme points, our principle, okay? It's not just where the derivative happens to be 0 or undefined. It's where the derivative is 0 or undefined and the slope changes sign, okay? And let me go ahead and give you a counterexample for it being undefined, okay? Well, let's just go ahead and take the inverse of that particular function up there. Y is equal to the cube root of x. Well, y prime is equal to 1/3 x to the negative 2/3, or of course 1 over 3 times the square root, or cube root of x squared. Where is this undefined? Well, it's undefined at 0. Because if you plug in a 0 right here, you get a 0 in the denominator, and therefore the derivative is undefined. So if the derivative is undefined, it isn't necessarily an extreme point either, because here it goes positive, the slope goes positive, 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 undefined positive, 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 positive. Okay? So our principle actually winds up being rather straightforward. It just has two aspects to it. Okay? So, extreme points for a function they have two parts. One, where the derivative is either equal to 0 or undefined. Okay? And the slope changes sign at that particular moment. Okay? So two things need to be the case. I need to have a derivative equal to 0 or undefined, and the slope needs to change sign. Okay? Well, these those aren't always extreme points, but I do have a special name for them. Okay? The special name for those are critical values or critical points. Okay? So think of, if you're ever doing your homework and you see critical values or critical points, basically critical values or critical points are possible or potential extreme values. Okay? Possible extrema. And therefore, and you only know after you check for that second portion. Okay, well that's all well and good. But you're probably saying, well, that's really great, Mr. Ford, but let's go ahead and get to an example. That's where I really learn things. Okay, you've convinced me. Let's go ahead and do an example. Now, if I have y is equal to x cubed minus x, okay, and I want to find the extrema. Okay, well, I happen to know something about that I learned back in Algebra 2. I happen to know, since that's a polynomial function, it is continuous on its whole domain, but it's also differentiable on its whole domain. So I know I'm not going to be looking for values where the derivative is undefined. I'm going to be looking for where the derivative is equal to 0. Okay? Well, the derivative is equal to 0 at x is equal to plus or minus the square root of 1/3. Okay? And of course, that would be root 3 over 3. And if root 3 is 1.732, then that's a little bit shy of 0.6, plus or minus 0.6. Okay? Now, what I need to do in order to determine which one is the maximum and which one's the minimum is I need to actually do what's called a sign chart. Okay? Now, you ought to know which one's the maximum, which one's the minimum, because you happen to know the shape of that. First of all, you should know how to factor that to find the zeros. Second of all, you should know what the end behavior is because it's an odd degree polynomial function with a positive leading coefficient, okay? But here's the thing. If you're actually asked to find the extrema, the person who assigns you that problem wants to see the calculus. But they didn't say that you couldn't know the answer ahead of time based upon your Algebra 2 knowledge. So make sure that you're bringing all of the resources to bear on any particular problem. I know that that factors into x, x plus 1, x minus 1, giving me zeros at -1, 0, and 1. Okay? So that function should look, oops, I missed -1, but you get the idea. It goes like that, okay? So this one right here at -√3/3 is going to be your maximum. This right here at +√3/3 is going to be your minimum, okay? But what I need to do is I need to actually dump it into what's called a sign chart, okay? And of course, we'll do this for training wheel questions, and then we'll do it for actual real questions. So I need, or ones that actually you don't know ahead of time, okay? Always good to do the training wheel questions and then get to the big bad ones, okay? Now, I'm going to basically carve this up. Oh my gosh, sign charts. That sounds so familiar. Okay. Up here, I'm going to put my intervals. Down here, I'm going to put what values my derivative function has. So my y prime values are down here. Now, those critical points carve this interval up into 3 pieces. And I express them in terms of interval notation. -infinity up to this critical value, up to -√3/3. The values in between the critical values from -√3/3 to +√3/3. And then the values from √3/3 on to infinity, right? Well, like I said, I already know or should know what that function looks like. I know that these values give me the derivative equal to 0. That's how I found the values, right? By setting the derivative equal to 0 and solving. So those are no-brainers. The question is, what do I do here? Well, just like you always did with sign charts, you basically plug in a representative point, okay? Well, you happen to know that that has a magnitude of less than 1, so -1 is on this interval. What happens when I plug in -1 into the derivative? Well, -1 is going to get squared. It's going to be +1 times 3 is 3 minus 1 is 2, so it's positive. So I know that the derivative is positive on that interval. Okay, well, I happen to know that 0 is a representative point on this interval. So I plug in 0 into the derivative function, and I'm going to get a negative. And then I'm going to take +1, which is on this interval, and the same thing is going to happen for +1 that happens to -1. I'm going to plug in 1, squared is 1, times 3 is 3, minus 1 is 2, so that's positive. And you can actually use this sign chart, positive slope, 0 slope, negative slope, 0 slope, positive slope, and I have the general contour, okay, of the function itself, okay? So based upon the signs of y prime, I have the shape of y, okay? Now, it's not enough to actually do the sign chart and do a quick sketch like this. You need to interpret it, okay? Remember that finding extreme points has 2 parts to it. The derivative has to be 0 at that point, and the slope has to change signs. Now here, we see that this is a maximum because the slope is 0 at that point, and at that point, the slope changes from positive to negative. And you would actually write that out, okay? Now here, you see the fact that you have a minimum because the slope is 0 at that particular point, and that point happens to be a place where the slope changes from negative to positive. And you would actually write that out, okay? So that's actually how we go about finding extreme points. Now that, of course, like I said, was a training wheel question. Sorry about that. Training wheel question based upon, what you already know about polynomial functions, because we actually hit that pretty hard during the Algebra 2 year and reviewed it during pre-cal. A lot of that should sound familiar. There'll be a couple more videos on this, and we'll just run through some examples, from here getting on into big bad trig questions, and we'll wind up hopefully having a pretty good understanding of what it means to find extrema for any given function.